Okay, YouTube, in this next video, my module on probability, we're going to touch on a really important concept, and that's the concept of what we call complementary events. And so basically what I want to indicate here is that when we consider, say, an experiment in which things are random, likely to occur by chance, we could say that the set of all possible outcomes here, we could say, of course, is this sample space. And I'm using kind of a Venn diagram notation here, but within here we could say that it may be the same size as the entire sample space, it may be nothing at all, but we could say it might have some substance here. We're going to refer to this as the event A. And so we would say that this is the event space of A here, and it contains all the favorable outcomes for this event A. The interesting thing here is, I can't write an A, but the interesting thing here is basically we would say, and maybe just this, maybe. I'm going to write the A inside because I should. We'd say everything in here is A. Basically, we're going to say that everything that doesn't happen in the event A is what we're going to call A complement, or what we say is A bar. And so when we basically say what's the probability, that we get the event A in the first place, and what's the probability that we don't get A in the first place, and what happens when I add these together. The interesting thing here is that the probability of A is all of the things in this little bubble here, and the probability of A bar, that's all this stuff out here. But if you were to add those two likelihoods up, look what it adds up to. It adds up to the entire sample space, and the interesting thing about the probability of the sample space is that the probability of the sample space is 100% of your stuff. So I got a little early on the parenthesis there. We say probability of not A is the same thing as 1 or 1.00, and I love this formula. So let's just kind of try this on for size here. Basically, up here I've written when we sum all of the probabilities of all of the outcomes in the sample space, then we always have a sum of 1. And so considering, say, flipping a single coin here, we'll keep it real easy. Let's say I have a single coin experiment here. We say the possible outcomes are that I flip a 1 or I flip a 2, and here's the set of all possible outcomes. You could easily see then the probability that I get a 1 is a 1 out of 2. And actually, I'm not going to write probability of 1 and 2 here. I've already written them. We say probability of, I guess this is supposed to be flipping a coin. Why did I write 1 and 2? I suppose I mean heads and tails. We're not talking about a die here. Let's try this again. So we say the possible outcomes are heads and tails, but basically the probability of that we get a heads is a 1 in 2 chance because there's 1 favorable heads and 2 possible outcomes. Same thing with tails. So we have a 1 and 2, 1 and 2, 50%, 50%. If you were to take the probability of heads and add it to the probability of tails, in other words, add up all the probabilities of all of the possible outcomes in the entire sample space, then you would have 2 out of 2 in this possible case. But all of the time, you're going to have, in every possible case, 100% of your stuff. So that fact allows us to say that if we know the probability of an event A occurring, then we can find the probability of the complement of A. So let's talk about what we mean by the complement of an event. The complement of an event, when we talk about the complement of an event with respect to a thought experiment or probability experiment, we say that the complement of an event A basically just consists of all the outcomes that are not in the event A. And so we would say that this is denoted by A with a bar over the top, just a bar here, and we read this as A complement or A bar. And basically what you can read this as also as not A, everything but A. And so when we say that, hey, the probability of A, which is some event, and the probability of its complement getting added together add up to 1, it basically leads us to a result here that is pretty profound, and that says this. What if I were to take the probability that the event does occur and subtract it from both sides of this expression? What you would see is that we end up with a new expression. We say the probability of A not happening really is 100% of the stuff taking off the probability that it does happen. In other words, if you were to say this, we would say here's A, all of the A's. We say A bar. Let's take 100% of our stuff, cross out the A stuff, and look what you get left behind with. You get all the stuff you're interested in, which is not A. So this formula is worth memorizing. It's not hard to memorize. But basically it says take all of the whole sample space, subtract off the stuff in A, you get left with the stuff that's not in A. I love this. So basically what I want to do is I'm going to take you through an example here, and I'm going to have you do your own over here on the right. But basically, let's looking at this first example, look at what we have here. So we say finding the probability of a complement of an event. When 2 6-sided dice are rolled, there are 36 possible outcomes as shown. And so this part of the reason why I want to do this example is because when you go through probability units, you do a lot of problems that involve games. So rolling dice, flipping coins, pulling cards out of a deck of cards, pulling marbles out of a hat. So what I want to look at is a situation where we have two dice being rolled, and instead of me saying, here's my tree diagram, first roll 1, 2, 3, 4, 5, 6, and then having 6 branches that come off of all of those, what I'm doing is providing you with this nice convenient table here. So don't lose this table. The nice thing about this table is that it's really kind of arranged very nicely. We have all the 1s in this column, 2s on the first roll, 3s, 4s, 5s, 6s. And you can see on the second roll we have 1, 2, 3, 4, 5, and 6. You can see here are all 36 possible outcomes in the sample space. So here are the probabilities we want to find. And you'll notice that on each of these we're going to say things like not, like not each of these, but on this one here we start with this word not. So we say the probability that the sum of the two dice is not 6. So we're going to say for letter A here, let's write this out first symbolically, probability that it is not 6, not a sum of 6 to be specific here, a sum of 6. So I'm going to write this way, but I also want to write it this way. Maybe I'll write it down here. We say the probability that the sum of 6, and then we're going to put a little bar over the top. And basically what this means is the complement of the sum of 6. And so if you've ever looked at this before, or you're looking at this now for the first time, we talk about the sum of these two dice. We say, okay, well, you're adding them together. And the interesting thing here is when we say a sum of 6, I could say, well, point out one possible instance of a sum of 6. I would say that, here's a sum of 6. You'd roll a 1 or 5 as a 6. But the interesting thing here is if you look at this next one, we say 2 and 4, 3 and 3, 4 and 2, 5 and 1. The nice thing about having this table at your disposal is basically you could see all of these sums occur on the diagonal. So we could say that there are 5 favorable outcomes that give us the sum of 6. Well, if we're going to find the complement then, let's try this again. I believe I accidentally just hit a button here. I think we can pick up from right here. Basically, a sum of 6, we could say there are 5 possible outcomes, but there were 36 total. So the probability that we don't get a sum of 6 in general is equal to the probability of 1 minus the probability that we do get the sum of 6. And so what makes this a little bit easier for us is we could say 1 minus the probability of sum of 6, and that's what I mean here. We say sum of 6. We could say there were 5 possible outcomes here that gave us a sum of 6 out of 36 total. And so the other nice thing is that we're taking it off the whole sample space. It means that we're subtracting from 1 and that we'll always have a convenient time of finding a common denominator between this fraction here and our 1. And so we'd say basically 36 possible outcomes, take off these 5. You get left with the other 31. So we say the probability of this occurring is a 31 in 36 chance. We also want to express this as a decimal. So we say 31 divided by 36 out to about 4 places here. And we'll talk about why 4, but 0.8611. So we're going to write squiggly squiggly 0.8611, so approximately 0.8611. And then the reason why we're talking about giving a decimal out to 4 places here is because we could express this now as a percentage, 86.11%. So pretty likely to occur that you're not going to roll a 6. So taking a look at this next one here, we say the sum is less than or equal to 9. So what I want to point out here is that we would just write down first of all, we say probability that the sum is less than or equal to 9. And that would be equal to 1 minus the probability that the sum is now not less than or equal to 9. And so we would say not less than or equal to 9, basically not less than or equal to 9. We could look at this. Let me cross out this really poor sum here. Is that the sum is at least greater than 9. We say greater than 9. And the reason why that's helpful here, we would say that, well, where are the sums 9 at in the first place? We have 9, 9, 9, 9, and we would say greater than or equal to 9. That would just be these, or not greater than or equal to, but just greater than. And so we would say there are only 1, 2, 3, 4, 5, or 6 of these. The neat thing here is we could say 1 minus 6 out of 36 chance. And I'm even going to reduce that. We'd say a 1 minus 1/6 chance, which is a 6/6 minus 1/6 chance, which is a 5 6 chance. And so sorry for the runaround here, but we need to get a decimal, and I don't have a lot of room. So we say 5 divided by 6. We would say 0.8333, 0.8333, box it. And this is also an 83.33% chance of theoretically happening. And so what we're going to do here is have you try this now with complementary events. We say use this diagram right here to find the probability of each event when 2 6-sided dice are rolled. So the sum is greater than or equal to 8. see what you end up with here. Pause the video, give it a shot, and then unpause it, and let's talk about this. So we say that the sum greater than or equal to 8. Probability that the sum is greater than or equal to 8. That would be the same as 1 minus the probability that the sum is basically not greater than or equal to 8. And that, to say this another way, would be less than 8. And so we would say, well, where are the sums 8? I notice that a sum of 8 is going to occur down this diagonal here. So we say 1, 2, 3, 4, 5 of those there. We say sum is less than 8. So everything to the left of this, you can see that basically this splits the table here. So we get, half the table on the left, half the table on the right. What that means is, this is going to end up being 1 minus an 18 out of 36 chance, which leaves behind 1 minus 1 half. So 1 minus a half, which is a half. So we have a 50-50 chance. We say that's 0.50, and save yourself some time there. You don't have to put it into a calculator, 50% of the time. And so we'd say, how about the sum is not 2? Give this one a shot. We'd say probability sum of 2 bar, we could look at it this way, not 2. It was 1 minus the probability that the sum is 2. I can write an M, I promise. SUM is 2. And so we say, well, how likely is it you get a sum of 2 here? Well, the sum of 2 only happens one time. Kind of nice. So the probability you're going to roll, anything, it happens one time out of 36, anything but a sum of 2 is pretty good here. So we get a 36 minus a 1 in 36 chance, which is a 35 in 36 chance. So box this, and then get yourself a decimal here. Get your calculator back out. 35, okay, divided by 36 is pretty good, a 97.22% chance. So we'd say approximately, squiggly, 0.9722, and that's a 97.22% chance of occurring theoretically. Cheers.